Take 25. Hey everybody, it's Mrs. Cassell. I'm going to go through the derivation for the UAM, or Uniformly Accelerated Motion equations we looked at in class today. A reminder, when you watch a video, you're free to pause at any point in time. You can also fast forward if you totally get what I'm saying and you need to skip ahead. Or, remember, you can press the rewind button so you can go back and review something that I've already covered. Also, I'm not offended if you just want to watch me do math and not listen to my annoying voice. So, uniformly accelerated motion is a situation in which that acceleration at any given point in time is constant. So that's an important thing. We only can use these equations in situations where there is constant acceleration. So, we're going to derive a couple useful equations that can be applied to motion situations. The first equation I'm going to do is I'm going to write down my equation that you already have in your notes for average acceleration. It's the change in velocity divided by the change in time. Well, I know that anytime I want to calculate the change in something, it's going to be my final quantity minus my initial quantity. What I want to do right now is I want to solve this expression for final velocity. It's useful to know, if I apply this much acceleration, how fast will I be going some unknown or some known amount of time later. So if I take my algebraic expression here, I've written it out like this. I'm just going to rewrite it so it's right here. First thing I want to do is get rid of that delta t on the bottom. So I'm going to multiply both sides by change in time. Now I have that my acceleration times my change in time is equal to my final velocity minus my initial velocity. Well, again, I want to solve for final velocity, so I'm going to add initial velocity to each side. Gets rid of that. And then I'm going to flip, which is where, just because I like to be able to have my expression read from left to right. Final velocity is equal to initial velocity plus acceleration times my time interval. That is our first equation. All we did was algebraically rearrange it, starting with our definition for acceleration. The next thing we're going to do is I'm going to make an equation we're going to use a little bit later to substitute in one of our equations, combine with this one. I'm going to take my equation for average velocity. Average velocity is our displacement divided by our change in time. And I'm going to do the same rearranging for this one. So if I rewrite that, I'm going to remove my time interval from the bottom by multiplying both sides. I'm going to get rid of that initial position by adding it to both sides. So I'm undoing my algebraic operation. I'm going to flip this equation around so that the value I was solving for is listed first. So I'm going to use this equation in combination with equation 1 to find something new. Our first equation is about finding final velocity, but before we move on to use this random in-between equation, there's one other way that we can write average velocity. If you think about if you're going to find the mean or average of a data set, you do that by adding together the quantities. So if I want to find the average velocity, let's say I measure your initial velocity and I measure your final velocity. One of the ways I can find your average is I can say, all right, I'm going to take one of the velocities I measured plus the second one, and then I'm going to divide by the number of things I added, which in this case is 2. So go ahead and put a box around this equation. This is the second kinematics equation, or UAM equation, that we're going to use. I told you in class today this is the least used in my opinion. It's sort of an essential, that's off the screen. It's sort of an essential equation to completing our algebra. But the reality is that very rarely are you going to have a situation where you know the average velocity and you're going to try to solve for the initial velocity in that case. We'll do that in some of our early problems, but you probably won't use it after our first few weeks working with these equations. So, here is where things are going to get a little crazy. I'm going to ask you to solve an equation that will be equal to final position. To do that, I'm going to use all three of these equations that I've written down so far. Equation 1, this in-between equation right here, and equation 2. To do this, I'm going to use substitution. I'm going to start with my equation in green. Right? Here's my green equation. I just rewrote it. I want to solve this equation and include other values such as acceleration, because right now this equation doesn't tell me anything about how much acceleration is taking place. So what I'm going to do, I'm going to do two different things here. The first thing that I'm going to do is I'm going to take this equation for average velocity, and I'm going to substitute this into here. So that looks like this. Final position equals initial position plus final velocity plus initial velocity divided by 2 times my time interval. Sorry, there's a smooch right there. The next thing I'm going to do, I have a final velocity right here, and I have one way up here. I'm going to take this final velocity and substitute it in right here. Makes it messier, but this is like cleaning your room. There's a point at which it gets worse before it gets better. This looks like final position equals initial position plus, and now we've got many parentheses, right? Initial velocity plus acceleration times our time interval plus initial velocity. All that's divided by 2, and there still is a delta t on the outside. I'm going to pause and flip to the other page by magic. Okay, now that I have a new piece of paper, at this point, all that we're doing is following the rules of algebra to move from one place to another. So, I'm going to do a couple things here. First, when I've got quantities that are being added together, the order in which I do that doesn't matter. So I'm going to get rid of these parentheses right here. Now I just have initial velocity plus acceleration times time plus initial velocity on the top. Well, I got two things that are initial velocity, so let's combine those. One initial velocity plus another is 2 initial velocity plus acceleration times time divided by 2, and I have another time interval outside. Second thing I'm going to do is this time interval on the outside is throwing me off, so I'm going to distribute it to the two terms inside my parentheses. Final position equals initial position plus 2 initial velocity times time plus acceleration, I guess those are all averages, I should put those back on there, times interval squared. divided by 2. Next thing I'm going to do, this 2 underneath, well, I'm going to apply it to my 2 terms in the numerator. Another way to think about that is, instead of having it down here in the denominator, I'm going to distribute 1/2 to each of the 2 terms in my parentheses. One half times 2 is 1, so that's initial velocity times plus 1/2 times average acceleration times time squared. Put a box around this equation and give yourself a pat on the back. That was hard. The fourth and final equation that we're going to use has perhaps the messiest algebraic solution. There are going to be times when we do not know the time interval involved, and so solving this equation for where we are or how fast we're going is really difficult because we cannot measure time or it is unknown based on other circumstances. So we're going to be looking at our equation number 1. Final velocity equals initial velocity plus acceleration times our time interval. I want to solve this for time. Solve this for time. All right, to do that, I'm going to add my initial velocity back to each side. Oh, sorry, I'm going to subtract it. I know what I'm doing, I swear. I've got final velocity minus initial velocity. It's equal to average acceleration times time. I'm going to divide both sides by average acceleration. Cancel that out. So I have an equation here that time is equal to my final minus my initial velocities divided by my average acceleration. So here's where this becomes a giant yucky. I want you to take this equation and substitute it for time in equation number 3. This is a long and elaborate mathematical derivation that I assigned for your homework, so I'm not going to do it in this video here. I'll do it in a separate video that I'll post later today. The solution to this equation is your fourth and final kinematics equation, which says your final velocity squared is equal to your initial velocity squared plus 2 times your average acceleration times your displacement. This is your fourth and final equation. All 4 of these will be incredibly useful to us as we analyze the motion of objects. Thanks, everybody. Have a great day. We'll see you in class.